Hi everybody, in the last video I introduced you the chi-squared analysis. Now in this video we're going to calculate one from start to finish, and then we'll also interpret it, so we'll see how that goes. Okay, really quickly again, a chi-squared analysis simply looks at a pattern in a set of categorical data, and then it says how well does this seem to fit a theory about how the data should fall. Okay, that's a very quick basic idea of what the chi-squared analysis does, but hopefully it'll make more sense as we apply it to a scenario here. So we're going to now calculate the simplest kind of chi-squared analysis you can do. It's simple because on the one hand we have only one variable, so we're looking at a chi-squared analysis with only one variable, and this particular variable has the fewest possible values that you could possibly take on if you're a variable, right? We'll have only two levels on this variable. You can't have one level of a variable because then by definition it's not a variable. It can't vary. Okay, so we're going to have just two options here. This was the scenario that I introduced in the previous video, but I'll give it to you again right here. So we've got somebody named Terry, and Terry has these two best friends, we'll say, and she's curious about, does one of them have a higher likelihood of being the first to contact her every day? And maybe she's judging her friendship by that. Whatever, poor Terry. So let's see what she does here though. So she's going to keep track of these friends for 28 days, and then she's going to decide to stop then. So let's imagine that there are essentially two options here, right? Either both friends are just as likely to contact her, to be the first ones to contact her any day. So that'll be our default hypothesis. In other words, the probability of one of the friends contacting her is the same as the probability of the other friend being the first to contact her, I should say specifically. That's not the same thing as probability of contacting her, but being the first one to contact her. Right, that's the null hypothesis we covered last time. And again, we're not interested in means, we're not interested in anything like that, we're interested in the probability. So if our theory is that neither friend has a different probability, this is what we should see. We should see that the frequencies, or the probabilities essentially, of either friend being the first one to contact her aren't different. Now, because it's 28 days, this is what her data would be expected to look like, right? We would expect Gina, one of her friends, to contact her 14 times out of those 28 days, and Rita to contact her, or I'm sorry, to be the first to contact her 14 times out of those days. Okay, now this is not what she saw in her real pattern, so let's take a look at the real pattern that she actually observes. Here is what Terry actually saw. In other words, Gina was the first to contact her on 16 of those 28 days, and Rita was the first to contact her on 12 of those 28 days. Now the question is, we see Gina was the one who contacted her more often first. That's not the same thing as that she is more likely to have contacted Terry first. Okay, this is what we need the chi-squared analysis for. It can now tell us, does this now reflect a higher actual likelihood, or is it still possible we could see this pattern if the null hypothesis is still true? In other words, can Gina have a 50% chance of being the first to contact her, and Rita can have a 50% chance of contacting her, and we still saw this pattern? If so, then we don't want to reject the null hypothesis. Okay, that's essentially what the chi-squared analysis does. So now I'll show you how it does that. Let's see the equation. And here's our chi-squared equation. As you can see, it's relatively simple. It's also quite easy to calculate. So let me walk you through this just a little bit. This is the Greek letter chi. It looks very much like an X in the Roman alphabet, of course, which is what we normally use in English. However, the ends here are a little bit more curved, which indicates that it is that Greek letter chi. As you can see, it's squared. We always refer to it as a chi-squared because we square the value up here, and then we never do take the square root. And so the chi-squared value is always a squared value. Okay, in fact, just to get a little weird about this, I always call it chi-squared with a D there. Some other textbooks or people will refer to it as chi-square. That just kind of hits the ear better. But it is chi-squared because it's in the past. It's not something we're going to square in the future. We squared it already, and so it remains that past tense squared. Anyway, so what we do here is then we've got the sigma, which indicates that we're going to add up whatever is next to it. So all of the values that we obtain next to it will be added up together. I'll show you what that means in a minute. The observed cell frequency here, that is of course the value of the value that we actually observed in our data set. that we collected the information and we found that we saw it ourselves, as opposed to the value that we simply theorized. So in this case, we're doing it for every cell, and we're going to do it for Gina, then we're going to do it for Rita. We're going to take the observed cell frequency for Gina and then subtract the expected cell frequency for Gina. The expected cell frequency is here. Of course, I showed you that before. That's the theorized cell frequency if our null hypothesis is true. And if our null hypothesis is true, then they had equal probabilities of occurring, and therefore we would have expected to see them both 14 times to be the first one to contact Terry on any given day. Okay, now, so the expected cell frequency, as you can see, goes there and there. So we'll do that for Gina. Then we're going to square this difference up here. Then we're going to do the same thing for Rita, where we're going to take Rita's observed cell frequency, subtract the expected cell frequency for Rita, which is right here, divided by, square that, and then divide it by this. Okay, so we need to do this for both cells. Now I'll show you how we do this. Okay, so I've lined everything up here, and I've also color coordinated just to make it a little easier to follow, I hope. But here's what we've got. Now, because we have 2 cells in the sample, we need to do this for every one of them. As you can see, I've added in this plus sign because that's what the sigma indicated. The big sigma sign said we're going to add up each time that we have a cell, and we're going to do this for each cell. Okay, so as you can see here, cell 1, I'm just calling Gina, right? Cell 1 is Gina's value, and that's the observed cell frequency. I'm going to take away Gina's expected cell frequency. Wouldn't make any sense if I was going to compare Gina's observed frequency to Rita's observed frequency in this particular case. Because what I want to see is, does the pattern I'm seeing in my data differ from what I would have expected for those same data, right? Okay, so I'll plug those in now. Oh, yeah, naturally, really quickly, if I had 3 cells, now I would have one for cell 1, one for cell 2, and another one for cell 3, and I would need to add that in. But of course, I'll do some other examples in the future that have more than just 2 cells. Okay, so if I plug in the values now, of course, 16 is the observed cell frequency for Gina, so that goes right there. And my expected cell frequency for Gina, expected, was 14, which goes right there, and then right there in the denominator. Now I need to do the same thing for Rita. Rita's observed cell frequency was 12, so 12 goes right there. I then have to take her expected cell frequency, which was 14, and plug it into both places there in the equation. And now that's it. My math is straightforward. Let's see how that works. Okay, so here is everything plugged in nicely, just like I had. I've just removed the color coordination. Obviously, what we need to do first is what's in parentheses, because that's what the order of operations dictates, 16 minus 14, and then also we can do over here 12 minus 14. That, of course, gives us 2 over here, and then negative 2 over here. You'll notice in a chi-square analysis, actually a really nice way to check your math is if you just look at the numerators and ignore the squaring, you can add them up and get 0. Unless you've rounded in any way, you will always get 0 in those top ones. Just ignore that the squaring sign's there. Now, as long as you do that, then you can continue on and, of course, complete the math. So, of course, now we simply square these values. 2 squared is 4, and negative 2 is negative 2 squared is also 4. So we can then add across, because we have 14 and 14 on the denominator. A common denominator means that we can just add on those numerators to get 8 divided by 14, and of course 8 divided by 14 is 0.57. Now let's get to interpretation. Of course, before we can interpret, we need to understand the degrees of freedom for this test. Of course, this is the pattern we've been doing throughout all of these lectures. Okay, now for a variable chi-square, when we have only one variable, it's very easy to calculate the degrees of freedom. You simply take the number of cells that you had in your table, the observed cell frequency or the expected cell frequency, it doesn't matter because it's the same number of cells for either table, and you subtract 1. So in this case, we had 2 cells, didn't we? We had 2 cells, and so therefore 2 minus 1 is 1. In other words, we needed to know the value of one of the cells to also know the value of the other, of all of the cells, to know the value of the other cells, as long as the parameters of the cells are set. For example, we knew that there were 28 observations, and so therefore we needed to know only the value of one cell to know what the other value of the other cell must have been. Okay. In any case, now that we have the degrees of freedom, we have 1 degree of freedom for this particular chi-squared analysis. We now look in Appendix E of the textbook. If you don't have my textbook, you can find similar chi-squared critical value tables online. You can just Google those. There are also some websites that'll calculate it for you Doesn't matter how you find it, just make sure it's accurate. This is what it looks like in my appendix, however. In Appendix E, you'll see a big graph, of course, a big table, I should say, that looks very much like this. Now, what we're doing here is we're looking for a chi-squared value with degrees of freedom of 1, as I just said. And so obviously we're looking in these rows. We always start off with a 0.05 level of significance, and if we exceed that, that's fine, and then we can go on and say that it's even more significant than that, you could say. Now, of course, we're looking at a 5% level of risk of committing the type 1 error if we reject the null hypothesis, which means that our critical value, of course, will be right in this column. And as you can see, where those two overlap is 3.84. Therefore, what this is saying is with these characteristics of this test, if you have 1 degree of freedom for a chi-squared analysis, you need to have a chi-squared value of at least 3.84 before you can say that it is statistically significant. So did we reach that? Well, of course, our chi-squared value is 0.57, which isn't bigger than 3.84. So therefore, we do not have a statistically significant chi-squared value in this particular case. So now what we can say to Terry, it looks like Gina and Rita don't have different underlying probabilities of being the first to contact you. It's still perfectly possible that they both have a 50% chance of being the first to contact you on any given day. It's just that in this particular case, we happen to see that Gina was the one who contacted you more often as the first person in the day. But that doesn't mean that one's a better friend or not. Okay, so we cannot reject our null hypothesis and go along with our alternative hypothesis at this point. Now, a couple of really quick things. Your chi-squared value always has to be positive. It's impossible for it to be lower than 0 because we square all the values, okay? And I'll show you a few other tips as we get going on some other examples. I'll do those in future videos, however. All right, that's it for today. Thank you very much, and I'll see you in the future.